Good afternoon, ladies and gentlemen. It has been a long day for you, so I hope you have some energy to listen to me for at least half an hour or so. Also, we're changing the tune of the talks. Most of it has been about application of technology in our improving our life. And I will talk a little more about how to improve our mind in terms of at least what science has to say about who we are and what is our place in this world, in this universe. So I'd like to give you a synopsis so that you know where I'm going. Basically, I want to point out to you that after contributions from many scientists, both theoretical and experimentalist, now we have a pretty good idea for the first time about who we are, what is our place in this cosmos, how this could be utilized in improving our quality of life. And so all of this has been possible with a series of paradigm changes in experimental discovery as well as theoretical analysis of those experiments and predicting something. So I will not go into too much into the scientific part, but at least like to give you an example or some idea that we're not just talking about nonsense. Everything is pretty much typed down in terms of what I'm going to talk about. So probably most human beings, as we have been able to think, then we can trace our genealogy back to the first Homo habilis that came around 2.5 million years ago. And then we can actually trace our ancestry back to probably a single bacteria. But humans are the only one that has been able to think about not only who we are, but this question must have arisen in your life at one time or another. But only answer we had before was either through religion or philosophy. Both have some problem. Religion professes that the knowledge has been given, you shall not question. And so religion and regular religion and science really do not agree in that, because science is open-ended. The first thing in science is that you shall question. And philosophers always have been trying to answer. They give good arguments on one side, equally good arguments on the other side. So you don't know which one is actually true. But in science, there's a gold standard of experiment. If the experiment says this is true, which anybody can verify, then we accept it. So all of these experiments as well as theoretical intuition, like Einstein was not an experimentalist, but his intuition really has made is at the basis of most of the things that I'll be talking to you about. So in terms of what do we come from? Well, as far as we have been able to think, at the beginning, way back about 2 millennia ago, Democritus thought that everything is made of atoms, which are not divisible. But that idea fell on the wayside because Aristotle didn't like the idea. But about 200 years ago, Democritus' idea was revived by English chemist John Dalton, but still he thought the atoms are not divisible. But then towards the end of 19th century, almost the last decade, last few years, few things happened that really showed us that different paradigm exists. Atom is divisible. First, J.J. Thomson discovered the electron, which is a negatively charged particle, and also radioactivity was discovered, which means that atom is not stable, it's giving out radiation. And of course, all of these came together with Max Planck's idea of the quantum, that energy that we all are made of, everything is made of, comes in bundles. A quantum means quanta, how much? A bundle, not continuous, discrete amount. Like for instance, electron is a bundle of energy, but it's not what we have been conditioned to think as a particle. Like we always present this, by the way, I'm not advertising my book, but if you want to, I'm covering a vast subject, so if you want to know a little bit more about details, you'll find in this book, Codename God, has been going on since 2005 and is still quite popular. And so what I'm talking pretty much encapsulated in this book. So what we look at is a cartoon picture, so to speak, essentially. See, talked about the atoms, everything is atoms, but now we found the electrons going around the nucleus. But here we're showing electrons, a little tiny marble ball particle. We realized that is not true, because positive and negative charge attract each other, so electron eventually fall into the atom will be destroyed. How is it that the atom is stable? That was a big puzzle. What he found, that electron is not really a particle. It is actually a web of energy. And let me see. I'm going ahead a little bit more. What I was trying to give you an idea of, we have built many big, large machines, and this is the largest one, to find out more about the experimental verification of the experimental results and the theory. And this is a 27-kilometer tunnel in Geneva, European Center for Research. It's called CERN, Center for European Nuclear Research. And inside this tunnel, you'll see these magnets. And there actually, you create the coldest temperature on the universe, smaller than the temperature of the empty space. And also when they collide, these particles collide, they create the hottest temperature up to trillion degrees and where the particles are detected. Why do you do that? Because when you want to look at something with your what it's made of, usually with a microscope, but the highest resolution microscope uses electron microscope. But that can only go up to about this level of the atoms. If you want to go deeper, there is no microscope. But fortunately, physics at higher temperature is equivalent to physics at lower dimension, fundamentally lower dimension. So instead of microscope, this particle physics accelerator actually is a physicist microscope, because creating higher temperature, we try to study what would happen as you go down and down towards the fabric of space. And these are detected by these giant detectors, about 5-story high. This is called one of the detectors, CMS detector, and part of it was built at the University of California, where I am doing my research now. So I just wanted to give you one idea that there are many machines like this have been built, but this happens to be the largest. And this is where the latest particle called Higgs boson was discovered, and that was probably one of the most important things that we were missing for 40 years. Finally, we found it there. And so this is how we get into this inside this here this one proton is here, and these protons are made up quarks, the quarks and gluons, and also there is some neutral particle called neutrons. So the nucleus is made of protons and neutrons, and they are very tiny, 10 to the minus 14 meter, like 10 to the minus 12 centimeter. And the quarks are even smaller, about 10 to the minus 16 centimeter. But with these big machines, we have been able to find their properties. And so essentially what we're doing here, we're getting not only how the microsphere of the universe works. If you go down and down to fabric of space, we can study with these instruments. Also, it gives some clue about the largest of the large, the universe. Universe is the largest of the large. And it's amazing that it so happens that the smallest space, which we call Planck's dimension, that's nature's unit of measurement. That's where dimension stops, nothing lower than Planck's dimension. And the universe, of course, is 10 to the 27 centimeter large, which is, to give you some idea, we human are about the mid-size between the largest of the large and the smallest of the small. So we may be tiny, but if you look into the reality of the whole entire system, we happen to be about the mid-size between the smallest of the small and the largest of the large. And so getting back to the paradigm change, as I mentioned to you, that we found out that electrons really are not little solid marble particle, they're actually a wave packet acting as a particle. So if it is a wave, we have to describe it by a wave equation. Then this is a plot of the real part of this real and imaginary numbers, real part of the wave equation. So if you have a wave equation, you have to describe it with a wave, what you call wave function. And then of course you have to use not Newton's laws of classical physics, but quantum laws of motion, which Schrodinger equation. Looks a little clumsy, messy, but it does give a good, it shows that electrons are stable inside the atom because this wave packet under the influence of the proton makes standing wave, just like in a musical instrument. When you play guitar, there's a standing wave. You play flute, there's standing wave. Here in the atom, these wave packets make standing wave patterns like these. This is the hydrogen wave function, which is the simplest. You see, when these patterns form, then the atom becomes stable. Electron doesn't fall into the proton. So this is the simplest one. And as we go to higher and higher, larger atoms, then we have more atoms, more electrons, more neutrons and protons in the center. And now, so this is the way that we describe all of the other particles. We'll get to that in a minute. But at least you can see that this the electrons really is a kind of a cartoon depiction. It's actually standing waves, uh, as you saw there. So there are really no. See. So similarly, oops. Similarly, you see these marble ball-like protons and neutrons. They're really not exactly. It is just a depiction for our perceptual understanding. And again, the course the same way. They're all actually wave packets. And so that was one paradigm change in our thinking. The next one came out, the world's famous equation, E equal mc squared, Einstein's most famous equation. I'm sure most of you know about this equation. Energy is really mass times the square of the velocity of light, which is the limiting velocity of the universe, universal speed limit. And this was unfortunately, infamously proved by Hiroshima and Nagasaki, showing that there's no doubt that atom is really full of just a packet of energy. And now we have to go a little farther, because these electrons going around, simple hydrogen, for example, moves with a velocity about 1/100th of the speed limit of the universe, velocity of light. And so, in the more complicated atoms, actually inner electrons go almost 2/3 of the speed of the light. So you have to correct for this equation using Einstein's theory of relativity. And when you do that, then you come up with this little complicated formula, but you see there's mass term here, and this one doesn't have a mass, but the momentum. There's, for example, in a photon, the packets of light that's coming from you to my eye, and you can see, these actually don't have any mass. We know that photon travels with the velocity of light, it doesn't have mass. So how does it have energy? Because of this term here, this momentum gives its energy. So we have to use relativity with quantum mechanics to really describe the atom more correctly. And at the beginning, there a lot of work was going on. The person who actually solved this was Paul Dirac. And I had an opportunity of meeting him when I was a student, because I was a student of S.N. Bose, of the boson fame. The name that he was given, bosons, was actually by Dirac. So when I was a student of Bose in 1952, he came to Calcutta, and this is a little faded picture, but very dear to me. So I'm just going to show you that just sort of nostalgic. So Dirac actually solved for the first time an equation that combines special relativity with quantum mechanics. And the result was a more accurate description of these energy levels. And so that was actually what we were looking for. This is one of the, again, most elegant equation, but it's sort of written in the physicist shorthand. This Dirac operator here, d slash, actually is a big, long expression. Physicists know when you see that sign what it means. So this is Dirac's theory for the electron. Now, of course, what Dirac set out to do to find the relativistic effect on the motion of the electrons, he found that, but he was surprised that instead of 2 equations, he ended up with 4 equations. And that was very puzzling. What are the other two equations are telling us? It turns out that after 2 years of proposing many theories, stumbled across something totally new that changed our paradigm again. And what he found that those two other equations actually belong to antiparticle. It seems that electron, the electron has an antiparticle, which is we call positron. So the two extra equations in Dirac's theory, they actually are describing, they're showing that matter is actually has every particle has an antiparticle, and what happens when they come together? They destroy each other, and energy comes out like a photon. So conversely, if you put enough energy, then you get a positron and an electron also. So if particle is not stable, what is stable then? Well, you got one pointer is that no matter where you create the electron in the universe, they have exactly the same property. Where or when you create is still exactly the same property. And so naturally led to the paradigm change of our thinking, that there is a field, continuous field, that fills all space and time throughout this whole universe. And they have not changed since the beginning of time. And so that's how we came to what we call quantum fields. The classical field you are aware of, this is like our classical gravity, which you do not see, you cannot touch, but it is spinning you down on your seat. But try to get up, then you would feel it. We go every day without even thinking about it, but it is unseen, untouched. You cannot touch it, but it's still there. But the quantum fields have a similarly abstract, no structure, no, you cannot see any form to it, but they have their own source. Earth's gravity has Earth is its source, but in terms of the quantum fields, they have their own source, and also classical gravity is stable, but quantum gravity is always fluctuating since the beginning of the universe, and everything has changed, but those fluctuations, the pattern of it, it is spontaneous, unpredictable, and always active, and there are many of them happening all the time, and that seems like a good source for manifestation of this of the universe. And so the quantum fields, and I'm just summarizing them, every particle have their antiparticle, and they all are particles can be created and destroyed. So we came up with this idea of the quantum field theory. That is the most intricate and yet most meaningful discovery, paradigm change or discovery that has happened in recent times. In the last 50 years or so, it has been developed. And so we have a standard model of elementary particles from the quantum field. So every particle has a quantum field, like electrons. Electrons has its own field. Neutrino has its own field. Up quark, down quark. So these are all called quarks, and these are the leptons. They have their own fields, each one of them. And then we have the gluon, which is the strong force. Then photon is our carrying the electromagnetic energy. And these are small. These are very small dimension, their interaction length, but nevertheless they exist. And then of course the Higgs boson. So we classify them according to their so-called spin. And so we have a complete model of these elementary particles that have been discovered, and all of them has exactly the fits in very beautifully with this theory. And so that theory happens to be very long, Even in physics shorthand, it's a pretty complicated, but you see here, these, these are for weak field, these for photon field, then we have the Higgs field, then we have the lepton fields, and then the quark fields, and this is gluon fields. So all of them, all the interactions are encoded in this one equation. And if you really want to get into it, you probably have to spend a whole career in quantum physics in a university. But fortunately, you don't have to go to it, but get the message, what it is trying to tell us. In science, as you know, it is open-ended. We know that quantum field theory of the Standard Model is established, but it is not the end. It doesn't have gravity, it doesn't have dark matter, dark energy, and maybe some other things. But at least in its own sphere, it will be always true, just like Newton's law. It's always true when the velocity is small, when the gravity is weak. But if you go to stronger gravity or very large velocity, then of course the Standard Model has to be modified. Exactly, we don't know yet how it will be, but at least we have room for it. But no matter what happens, just like Newton's law has remained true, the Standard Model will remain to be so. Now next paradigm change is that all of these fields that you saw, all of these particles, they all come from one source. What we have done is we cannot go to very high temperature, but we can go to we can utilize our theory to determine what would happen at higher and higher temperature. So if we do that, we find very interestingly that the strong force strength come down, and the electromagnetic force strength become higher. So eventually, at a high energy, they actually become one. And if you go a little farther down, then gravity will be united also. This is the most cutting edge area of research now, how to find unification of all the forces and particles. And so you see at the very fabric of space at 10 to the minus 33 centimeters, I mentioned, all the forces and the particles eventually unite. So now imagine this to be true exactly. It fills all space and time throughout the universe. How big is the universe? It's very hard, it's beyond our perception actually, but we know the Andromeda Nebula, which is Andromeda Galaxy actually, which is our closest neighbor. But even that is 2.5 million light years away. Light travels at the speed of 186,000 miles per second. So from Earth to Moon, it takes only 1 second, and one. It's time to go from here to there. If you just to go around the world one time, it's only 10th of a second, just flicker of an eye. At the speed, can you imagine 2.5 million years, the whole time that we have been evolving from Homo habilis to human? This light is only reaching our very first galaxy. And there are 2 trillion of these galaxies in our visible universe. And so immensely vast, but all of this space is filled with these quantum fields, bearing the blueprint of all creation, and also their activity is very similar to our basis of awareness, that it is actually providing the impetus for our evolution, and nature allows evolution of all the possibilities. For example, on this earth, 99.9% of the species that ever lived has been already extinct. We are the product of this evolution, and naturally we're the dominant species. And so we can really think about not only the same science that has given us technology. We live in a global technological society now, the same science is telling us that the whole universe is filled with this quantum field, and they're fluctuating. They're fluctuating. This is a slow motion description. If you go to higher speed, it will be almost blurry. It's really fortunate that universe has spared us from perceiving this, but nevertheless it is there. You can see all the effects through our experimental measurements, and this is to show that this fluctuation is exactly everywhere throughout the universe, no matter where you are not, and always active. And this is, we are in that sense the in a manifestation of this spontaneous activity of the universe, which is creating all the manifestation leading to our existence, and still controlling and upholding our life and our manifestation. And I just want to finish by pointing out to you that it's early to see that how similar this is to our ancient Vedic wisdom. In Sanskrit we say Sarvam Khalidam Brahma. Brahma, the formless source, exists being intertwined inseparably with everything. You, me, all the particles, everything is come from one source. And we are intertwined, inseparable in our existence with that. And that is something that we do not think about it, but eventually, as we evolve, that would, I think that paradigm would really give us a good understanding of what we are and what's our place in the universe. And also, obviously, this is Aham Brahmasmi Tattvamasi. I am the source, part of, inseparable part of the source, and so are you. So everything else in this world are interconnected at its deeper level. And this has a connotation that eventually will help evolving in our brain, as it has helped technology that is that really has made our lives so much easier today. So, in effect, this knowledge that our rishis got was through contemplations of many millennia. It's really strange to think that that knowledge, that the description that they gave of our origin, where we fit in this universe, is so eerily similar to what we're finding through science. Isn't that interesting? With that, I would finish my talk. Thank you.